So let's take a look at the last week's assignment together. Here we are asked to work on Poisson's equation, which looks something like this. If you look in the book, they say nabla squared of u is equal to f of x comma y for x and y in D, where D is the unit square, looking like this. So this is the unit square. So the first thing we probably want to talk about when we see this is, what is the weird upside down triangle? Well, the symbol is produced nabla, but the operator in itself with the nabla squared is what we call the Laplacian or the Laplacian. And it is a kind of shorthand notation that we use instead of the following here. So the Laplacian nabla squared is a shorthand notation, so it's just symbolic language for the partial derivative of u 2 times with respect to x plus the partial derivative of u twice with respect to y. So this thing is exactly equal to this thing here, nabla squared u xy. So no need to get too scared of this notation, and whenever you see this upside down triangle, this is what it means. Those of you who work with physics probably know it quite well already. Those of you who are actuarial students, math, econ students, or just pure math students probably haven't worked that much with this operator. But anyways, each time you see this, you just have to think about this thing over here. Okay, so let's just try to get to know this problem a little bit better, draw up where this problem is defined. So in this differential equation, we consider a domain consisting of the unit square in the two-dimensional space of real numbers. So what I have over here is, let's see, I consider x and y on the unit square D. So this is 0, 1, 1. I have my y-axis here. I have my x-axis here. And then the innards over here, this is D. Okay, so I want to try to solve this differential equation on the unit square D. Now, the first thing we can ask ourselves is, well, what do we already know? What do we know? Because apart from just the differential expression, we also know certain conditions that the solution u of x comma y must satisfy. We have some boundary conditions. And according to the book, the boundary conditions that u of x comma y should satisfy are as follows. Namely, that our solution u is equal to 0 on the boundary of D. So for all x and y that are here on the boundary of the unit square, we know that the solution is equal to 0. Now this is an unprecedented case, actually, because we've never worked with something like this before. In the previous weeks, we've worked with the heat equation, and we've also worked with the Black-Scholes. And in both cases, well, we did have certain boundary conditions and initial and terminal conditions, but in no case at all have we yet had boundary conditions that surround our whole domain. In the case of the heat equation, well, we had the two edges over here, and then we had some initial condition down here, and then we worked our way up in this direction. For the black shoals, we had a starting condition over here, and also one over here. So we had the boundary conditions set, and we had a terminal condition for time capital T up here, and then we worked our way down as such. But now what we actually have is a unit square domain where the boundary conditions encase our domain, which actually means that when we try to solve this problem, we won't just work our way up or down, we're actually working our way inwards all at the same time. And actually what this means is that we will end up solving this differential equation numerically by solving a complete matrix all in one go. So we will solve this whole thing at once, and that will be pretty interesting. Just to round this off, to get you guys started, well, so what is it we want to solve? We want to solve the Laplace, not the Laplace, we want to solve the Poisson equation, which looks like this. And what we are asked to do in the book is to find a finite difference approximation, which has, so find finite difference approximation, which has a truncation error that has the same order of magnitude as O to the h squared plus O to the k squared, O of k squared. What did I just say? Truncation error with the same order of magnitude as h squared plus k squared. That's what I wanted to say. Okay, so Poisson's equation is what we want to solve, and it looks like this. It's the second partial derivative with respect to x plus the second partial derivative with respect to y of u equal to f of x comma y. And in order to find inspiration to do this over here, well, I suggest that you look in the book on page, no, I'm not sure which page it is, but it's section 6.2, where we have a finite difference approximation of another differential equation that looks very much like Poisson's equation. In the book section 6.2, we study the Laplace equation, which looks exactly like Poisson's equation, but it's a special case of it in the sense that we set the right-hand side to 0. So the Laplacian of u equals 0. And then they solve this thing in the book. So that's where I'm going to leave you guys, and in the next videos we will try to solve 618a together, more or less, where I will try to explain how we work out the finite difference approximation of this problem inspired by the method they use in the book, and also we will try to look at how we write up the matrix equation.